So you get this down to your notes, and then as you're writing it, I hope that you're finding that it feels a little familiar. You may recall from yesterday something here. What do we call it in a special case if f of a equals f of b? Well, notice if f of a equals f of b, that means when we subtract them, that'll be 0. So the derivative would equal 0 in that case. What do we call this thing when it deals with it being 0? If you look back at your notes from yesterday, you would see that we call that Rolle's theorem. Rolle's theorem that we were practicing in our last class was really just a specific case of the mean value theorem. It was just the very specific case where we're looking for a derivative of 0. And it's all because the two heights of our endpoints are the same. So the slope between them is 0. It's just we're seeing today that we can extend that to any slope. Now just to illustrate what this is really saying then, you notice here is just some curve. It's just a random curve I made up. Now what this is saying is that at some point on the curve there should be a tangent line that has the same slope as the line that passes between A and B. Specifically, we can actually see that here. This blue line here represents the slope between A and B. You'll notice that between them on the curve, at least at one place, there has to be a point that has a tangent line with the same slope, and therefore a derivative with the same value. And of course, it can happen in multiple places at once, but all we know for sure is that it happens at least once between those 2 points. Now we're going to practice that with this problem. So go ahead and write down this problem. All right, now to answer this question here, we first need to see that it actually satisfies the hypothesis of mean value theorem. Now remember, there's only 2 things to do there in this case. Just like the Rolle's theorem, it's the same 2 that we started with there, except in that one we had to do one more step, one more check. In this one, it's just the first 2. The first of those is it continuous? Well, you'll notice that this particular equation, this particular function, is continuous across all points. Not even just those in our interval, but every point. So I can know that it's definitely continuous within our interval as well. Is it differentiable? Yes. Same kind of reason. This is differentiable at every point. And so it's certainly differentiable within those as well. All right, so knowing that now, I now can go ahead and find all numbers C that satisfy the conclusion of the mean value theorem. In other words, I need to find any numbers in which the derivative equals the original slope between the endpoints. That means I need to start by figuring out what is that slope. And so in terms of this particular problem then, that means I'm going to have to be figuring the slope by doing f of 1 minus f of negative 2 over 1 minus negative 2. It's the same slope formula we've always used here. Delta y over delta x. We're just being very formal about it here. But if you think of it as delta y over delta x, you're fine. You don't have to be this formal with it. All right, so I do need to figure out then what f of 1 and f of negative 2 are. So if I plug 1 in for x, I get 7. And then f of negative 2 is 1. And then on the bottom, 1 minus a negative 2, well, that's going to be the same as 1 plus 2. And so I end up with 6 over 3. So then my original slope then is 2. So then what that tells me is that there has to be some point in my derivative where x equals 2. And so then I go ahead and start that work. So first thing I got to do there is find the derivative. So f prime of x equals 2x plus 3. And I want to know when that has the same slope. So I'm going to do 2 equals 2x plus 3. And I'm looking to see where the derivative has the same slope. It's all about that connection right there. And so then we solve it from there. So subtract the 3 from both sides. That gives me 2x equals negative 1. Divide both sides by 2. We get x equals a negative 1/2. That is the c value that we're looking for. That value of c that satisfies the conclusion is x equals negative 1/2. All right, so taking a look at this problem, notice we're given some numbers that deal with velocities, the speeds, so like the 50 miles an hour and the 30 miles an hour over here. And we're asked when the acceleration hits a particular number. Well, we know, of course, that acceleration is the derivative of velocity. Now, knowing that then, this is going to end up involving taking basically, to find my slope, like a delta v over delta t. That's basically what our derivative is it's that slope of the velocity over time. Now I'm writing it using the delta notation here instead of subtraction because I think it's just a little bit more intuitive with these particular numbers that we're working with here. Because here, delta v, well, that means I'm going from 50 miles an hour to 30 miles an hour, so I can subtract those. But the reason why I like the delta notation here is because to me it's a little odd to write 2:10 minus 2 o'clock. It just doesn't make sense to me so much. So instead, I'm just going to go straight to what does delta t equal. But I don't want to use 10 here. Because you'll notice what time is measured in. Time is measured in hours here. So yes, it's a difference of 10 minutes, but 10 minutes equals how much of an hour? 1/6, yes. So I'm actually going to have that written as over 1/6. Now that I've done the setup, it's a matter of doing the math. So 50 minus 30, that gives me 20. So I'm going to be doing 20 over 1/6. Well, that's division by a fraction. And remember, to divide by a fraction, that's the same as multiplying by its reciprocal. Well, its reciprocal is 6 over 1. So that's just going to be 6. And so that gives me 120. Now this one they made a little bit easier on us. We didn't have to know the equation or anything like that. We just needed to verify that it had to be able to hit 120 miles per hour squared at some point there. And there we've shown that. We've shown that at some point it will have to have that acceleration.